Welcome back, guys. Now we'll start a new chapter, and this chapter is about electrostatic potentials and capacitance. Capacitance is like a different topic, and that's the second half of the chapter. So now let's talk about what is electrostatic potential. So in this video we'll cover two main topics, that is introduction to electrostatic potential, and secondly we'll talk about potential due to a point, which is a derivation. So first let's see what is electrostatic potential energy. So these are not the same words. These are two different things. One is electrostatic potential energy and the other one is electrostatic potential. So electrostatic potential energy. Let's compare this in terms of gravity or even mechanical energy. So let's consider there's this spring which is attached to the wall, and you have a block which is moving towards it with constant velocity v. So when this block comes and just compresses the spring, the next scenario is going to look like this, which is the spring is highly compressed and the block is pressing against it. That is, the spring moved from its initial position over here till over here by a distance of x. So this movement, this compression of the spring causes it to store some potential energy. That is, the kinetic energy of this block, which has some certain value to be k, at the instant when potential energy is 0, has been transferred to the spring. That means now the potential energy of the block is no more equal to 0. It has gained some potential energy, and for a spring it is half kx square. This is the potential energy of a spring. Same way, there exists energy, a potential energy in charges. So let's talk about potential energy of charges. Let's consider there is a positive charge placed somewhere in the space, in region. So let's consider it to be plus q. Now what we are going to do is, we are going to bring a unit positive charge, just like how we discussed. Point P is always a unit positive charge. So let's say this is at point P. And you know that a positive charge emits electric fields outward, radially. So it's going to be in this direction. The electric fields are going to be like this. So the electric field is trying to repel the positive charge, isn't it? Because let's zoom into this version. Let's just zoom in over here and let's see how's the scenario over there. So this is the positive charge P that we are bringing, and the electric field lines are in this direction due to this positive charge. So now let's just get rid of this diagram. Just don't think about it. Let's look at this electric field. Which side of the electric field is positive and which is negative? That is, this side is positive and this is negative. That means there is going to be a repulsion when you're trying to bring it together. You can also think of this as one positive and another positive. You're trying to move it towards the positive charge, which is not liked by charges. Positive and positive is supposed to repel. But against that repulsion, you are giving a force to bring it together forcibly. So let's say the force you're giving is equal to the opposite of the force that this is trying to push it away with. So what is the force this is giving? Which is Fe, the force due to the electric field. This is pushing it away with a force of Fe. And you are giving a force external, which is minus F external. The reason why these both are equal is so that the net force acting on the particle is 0 and it's moving with a constant velocity. The condition for constant velocity is sum of all forces should be 0 on that body. Or else if the force had a non-zero value, that means there exists an acceleration, which we do not want. And this, a charged particle, when it is being acceleration, then it will produce electromagnetic radiation. This comes under the electromagnetic theory of Maxwell. So that's why we are trying to avoid acceleration over here. So we are giving the condition that you are giving equal and opposite force so that it comes with zero acceleration or constant velocity. So let's say you are applying a force of the negative of the force this is providing, that is opposite direction. So in that case, this is being forced to move against it. So now let's define what is the electrostatic potential energy. The energy being stored in this charge due to the external force is known as the electrostatic potential energy. and we have one relationship, that is, let's say we are moving it from point P to point Q, and let's say the potential energy at point P is UP, and let's say the potential energy at point Q is UQ. Potential energy is denoted by the symbol U. So the work done in moving the charge from P to Q, work done in moving the charge from P to Q is equal to the potential energy at Q minus the potential energy at P. UQ minus UP. The difference in these potential energies is the work done. So this work is a conservative work. I mean the force is conservative. That means this work done will depend only on the final and initial position. That means whether you're bringing the charge from here to here directly in one go in a straight line, or whether you're taking this charge over here, and finally bringing it over here, no matter the path you take, the potential energy, the work done is going to have the same value, which is the difference between the final and the initial point. So this is the work done, and this is used in a lot of numericals, so it's something to be noted down. So after we are done with this, let's see what is electric potential. Okay, so now let's look at electrostatic potential. This is a different, slightly different concept from potential energy. So what we're doing here is, we know the formula for the work done, which is the difference in the potential energies, UF minus UI. But for, okay, so let's look at potential energy. The energy depends obviously upon the charge that you're bringing. That is, if the charge is greater, the potential energy is also going to be greater. If the charge is having a lesser magnitude, the potential energy is going to be less. To avoid this confusion, to avoid this dependence on charge, what we do is we divide the potentials by the charge to eliminate its dependence. That is, UF minus UI by Q. What this does is that now the potentials do not depend on the charge that you're bringing in. It only depends upon the, remember the main source, which is plus Q. It only depends on this and not on the positive charge that you're bringing. And that is the reason why we're dividing it by Q, to make it independent of the charge you're bringing. So this term is going to change. The potential energy divided by the charge is a new quantity, which is known as the electrostatic potential, V. Vf minus Vi is the, this is also work done, but it won't have obviously have the same magnitude as the initial case, but this is the one we use. So the difference in the electrostatic potentials give us a more accurate, give us a more convenient result. So this is the expression. So now what we can do is, we always have the choice of choosing which you want to be the initial and final positions. So let's say you need to find the charge, the potential at this point, which is at a distance r away. So how do you find that? You assume that you're bringing this charge from infinity. If you're bringing it from infinity to this point, it's going to be V of f minus V of infinity. That's the difference, right? The initial point was at infinity, and we make an assumption that the potential at infinity is 0. So it becomes the work done required to move a charge from infinity till this point r, where you have the distance r, is equal to the potential at that point. So this is the definition of electrostatic potential. The amount of work that needs to be done to bring a charge from infinity to a point in the given region is equal to the electrostatic potential of that point. So I'll write down the definition. This is the definition of electrostatic potential. The electrostatic potential at any point in a region with the electric field, that is, there must be something to oppose the force, then only the potential would build up. If there was no force, and if you're just pushing, there's no potential required. So the electric field is the work done in bringing a unit positive charge from infinity to that point, and make sure it should not have any acceleration. With zero acceleration, that is sigma f equals 0. This is the condition. So this is electric potential, electrostatic potential. So now let's derive the electrostatic potential due to a point charge. Okay, so if we need to derive, first let's assume the quantities we need. That is, there is a positive charge present over here, which gives the electric field we require to oppose the force. So we need to find the electrostatic potential at this point P, which is at a distance small r away from the main source. So to find the electrostatic potential at point P, we need to first bring the positive charge from infinity to that point, because we know the work done is equal to the potential at that point P we require. So this work done is the potential. So let's find the work done to bring it from infinity to this point. So first, what we are going to do is, we are going to find a location in this line, a small location, and find out how much work is going to be done to move it from that small location. And then we can generalize it for this entire path by integration. So I'm going to connect this line, and I'm going to assume a point in between, which I'm going to call it as Q. Since there is a Q already, I'll call it as an M. So this point M. Now this is on the way, okay? Let's see that the positive point is over here, and you're bringing it till this point P. So this is somewhere in between. The reason we need this is so that we can generalize it for this entire path. We're finding a small element. It's like you have this length, you're finding the small element over here, and then you're integrating it for this entire length. That's what you're doing over here. So let's consider this point M, and let's imagine that the positive charge is moving from this point M to a point M dash, which is very close. The distance M dash is delta R, which is a very small distance compared to the entire distance R with respect to the point M. Okay, so the diagram is done. I'll just explain the diagram once more. There is a positive charge Q, which is emitting out radiation, electric field lines, which opposes the movement of positive charge. We need to find the electrostatic potential at point P. And from the definition we just saw, the potential is equal to the work done if we were to bring a positive unit charge from infinity to that point P. So this is that travel distance from infinity to point P. But we do not know how does it travel. So we are just going to assume a point over here and a point very close to it, that is M dash. And this point M is at a distance capital R away. So this distance is very small compared to R, so we are calling it delta R, which is a very small distance. So let's see how it goes. The work done, you know the formula for work done, which is just force times displacement. But what about a small work done? Because they are moving it only by distance delta R, so we are calling it small work done is force into a small distance ds. So now let's substitute the values. What is the force? From Coulomb's law, K, Q1, Q2 by R square. K, Q1, which is positive Q, but this is a unit positive charge. So the value of Q, the second Q, K, Q1, Q2 by R square. So this Q2 has a magnitude of 1, so we don't need to include it in the formula, divided by R square, where R is the distance. We are considering it for this point. This is not for the point P, this is for the point M. For point M. Because we are first finding the work done to move from M to M dash. After that, we are going to generalize it for the entire path. So KQ divided by capital R squared into what's the distance it's moving? Delta R. That is the distance it has traveled. And now it's going to have a negative charge. And why is it negative? Because the displacement is in the opposite direction of the force applied. The electric field lines are in this direction. The force is in this direction, whereas the displacement delta R is in the opposite direction. So this is going to have a negative charge. So all that's left now is to integrate. But what are we going to integrate? From where to where are we integrating? So the total work done is equal to integral. You're bringing it from infinity to point P. That is, this is the general. At any location R, this is going to be the small element of work. Now we need to find the total work. So we are integrating it from infinity to the location of this point P. That is from infinity to distance r. We are looking at with respect to this. Consider this to be the origin. That is, it's located at 0, 0. Everything is with respect to this positive charge q. So this distance is r and that is infinity. So infinity to r of minus kq delta r by r square. This is work done because integral of dw is w. I'll write it over here. Integral of dw equals w. So now we have to integrate this, and there's only one formula you require for most of the integrations in the physics portions. That is integral of x raised to n. Here's the formula. You must have used this in grade 11 as well. X raised to n is equal to x raised to n plus 1 divided by n plus 1. This is the formula. So what is the x over here? K and q are constants. You have to take them out. So r square is the variable x. So I'll just erase this off. So all that's left now is to calculate it. So I'll rub off the diagram as well. Okay, this is what we have. Delta r is a small distance of r, so we are going to just write it as dr. You have learned this concept where you limit a certain quantity, like for example delta q divided by delta t. With the limit delta t tends to 0, that is, when you're approximating this to be 0, it is the same thing as the value of differential of dq by dt at that instant. dq by dt means it's a very small quantity, it's at that instant, and that is what you're trying to do here. You're trying to find out the potential at that instant. So here we can just apply the concept of derivatives, so it becomes dr. Now k and q are constants, you can bring them out. So minus kq integral infinity to small r square is r raised to minus 2. So now we have to integrate this, and we saw integral of x raised to n dx. dx is always going to be there. So it's x raised to n plus 1 divided by n plus 1. So let's apply minus kq r raised to minus 2 plus 1, which is minus 1 divided by minus 1. And do not forget the limits are there. That is from infinity to r. So this, my negative sign, is a constant. So you can just take it out instead of dealing with it inside. So when you take the minus 1 outside, this negative and this negative cancels off. So you're left with kq r raised to minus 1. I'm going to write it as 1 by r from infinity to r. Now we know how to apply the limits, right? Upper limit minus the lower limit. So it becomes kq 1 by small r minus 1 by infinity. 1 by infinity is 0. So you're left the final answer being work done equals, I'll write it on the top. So I'm going to erase this again. We have work done equals kq divided by r. You can substitute the value of k, that is 1 by 4 pi epsilon naught q by r. And this is the whole point of why we divided by that positive charge q in the formula for potential energy. So that the work done is independent of the charge you're bringing. You can see that here the work done, which is equal, the final answer is not yet done. That is, we need the answer for potential, but the potential is equal to the work done. So the potential equals 1 by 4 pi epsilon naught q by r. It no more depends on the charge you're bringing. It only depends on the configuration of charges you have to which you're bringing another charge. So this is the value for potential. Now if you notice, you can make a clear relationship between potential and electric field strength. So this is potential, you can note it down. Now this is potential, and the formula for electric field was 1 by 4 pi epsilon naught q divided by r squared. So how do you make a relationship out of these both? That is, if you multiply the electric field by distance r, you get potential. So this is a relationship, that is potential difference equals the electric field times the distance of separation. V is equal to ER, electric field times R. So this is how you convert between potential energy and electric field. So yes, if you need to draw the graph, this is both the graphs are reducing graphs. That is, as the value of x-axis increases, the potential decreases. But there's a small difference which is an important differentiating characteristic feature. That is, the electric field is a more steeper graph compared to the potential. So if you draw the potential graph to be this way, V as a function of the distance, the electric field is going to be a steeper graph. So this is the electric field. So these are the values, graphs for potential and electric field. So with this, today's topic is over. In the next video, we'll see about the further concepts. That is, we'll talk about how to express this in terms of gradient. It's a differential gradient. After this, we'll have the derivations for electric field. Potential at any point along a dipole. Just like how we did for electric field along the dipole, the same thing is repeating for potential, and you'll see how it's similar. Okay, so thank you and see you on the next video.